All right, number 3 on the quiz, be less drawing on this one. Simply ask what the relationship was between the two molecules. So what is the relationship? Sounds like, something you'd be gossiping with friends at lunch or something. Two molecules are always going to have some sort of relationship. They can be completely different molecules, but they're still molecules, right? So we talk about them the same. They can be isomers of some sort. So completely different molecules would be different molecular formulas. But they could still have a relationship. They're both amides. They're both polar. They're both, they both cross the blood-brain barrier. Whatever. You can always find somewhere that molecules have something in common. So, really, in the early days of this class, what is the relationship between two molecules? Simply means what's their isomeric relationship? Are they different? Are they constitutional isomers? Are they stereoisomers? I actually didn't give any options there. They can be stereoisomers. We're going to talk about stereoisomerism pretty quickly. Conformational isomers. Okay, so first, are they isomers? Do a molecular formula. You've got 4 carbons of the cyclopropane on the left. 1, 2, 3, 4. C4. We've got 1 oxygen. And there's 1 unit of unsaturation. Okay? Over on the right, C4. 1, 2, 3, 4. 1 oxygen and 1 unit of unsaturation in the pi bond. So this is going to tell you that they're isomers of some sort. They have the same molecular formula. I'll prove that. Let's go ahead and count. I'll draw in the hydrogens. All right. So 1 on the oxygen, 2, 3, 4, 5, 6, 7, 8. So this is H8. Drawing hydrogens over on the left. 3 on the methyl, 2 on the methylene in the middle, and then 3 on this methyl here. 1, 2, 3, 4, 5, 6, 7, 8. So like I said, you can do it a lot faster if you don't need to count the hydrogens. Count the number of heavy atoms, non-hydrogen atoms. Count the number of unsaturations. That'll get you there. So they're isomers of some sort. So they're not different molecules. So now you have to figure out what it is. And the isomers you know so far, here are the options. I don't know if you really know stereo. I've mentioned it in class. So, constitutional isomers are connected differently. Okay, there's no way to simply rotate around a bond and make the two structures the same. So you have to break bonds in order to make those two structures the same if they're constitutional isomers. Conformational isomers, on the other hand, you can actually go back and forth between the two structures simply by rotating around an allowed single bond, right? So single bonds have free rotation. So if the two structures only differ in their rotation around a single bond, they're conformational isomers. Stereoisomers, sort of in between. They're connected the same, okay? So, but they, in 2 dimensions, if you just draw them flat, if you don't put any 3-dimensional stuff into the structure, the two molecules would be connected the same, but then they differ in how they're arranged in 3 dimensions. We'll talk about that. Don't worry if your stereoisomers are confusing you right now. We haven't really done anything with it. But those are the 3 names you've heard. And so really what you have to figure out, you should assume I'm not probably going to ask you a stereoisomer question before we've really done some problems with it. So constitutional isomers, conformational isomers. The question is, can you go from the molecule on the left to the molecule on the right by rotating around a single bond? Okay, you clearly can't, all right? There's no way to rotate here. To break, well, first of all, the molecule on the right doesn't have a 3-membered ring in it. So in order to not have a 3-membered ring in it, you have to break a bond. I'd have to break one of the cyclopropane bonds to make the molecule on the right. All right, if I break a bond to make them the same, they're constitutional isomers. Same thing. There's a carbon-oxygen single bond there, carbon-oxygen double bond here. In order to make these two the same, I have to break the OH bond, and I have to break a CH bond. That's not allowed. So the answer is that these are constitutional structural isomers.